Hello and welcome to another class of ATMO 620. I hope you're all doing very well. I hope you're staying inside and staying healthy. Today we are continuing our journey into cloud microphysics, into the discovery of cloud microphysics. If you remember the last few lectures, we started introducing first of all, we introduced water vapor and the effects of water vapor on the air. And then we started talking about what happens when there's, quote unquote, too much water vapor in the air. What happens when we reach what we call saturation. And we started talking about the formation of cloud nuclei, okay? Cloud condensation nuclei. In other words, we started talking about nucleation. And then we introduced, recently, the growth of nucleated droplets by condensation. Today we'll continue discussing that, and then in the next few lectures we'll introduce rain, the formation of rain, ice and snow, and so forth. Okay, so what do we want to talk about today? Last time, if you remember, we introduced an equation that is a very important equation that tells us how the radius of a droplet grows. This can also be written as changes in the square the radius as a function of the supersaturation over some terms that we wrote last time. We don't need to get too much into the specifics right now. Anyway, this is all great. But notice how, in this case, we're kind of assuming that there is an environment that is forcing something to happen, and that has an impact on the radius of this droplet. However, you could imagine clouds, the clouds we're thinking about are made of many, many droplets, okay? And so you could expect that all these droplets would have an effect, because there are so many of them, they would have an effect on the environment, okay? You should expect that this is the case because these droplets are formed as a response to a condition in the environment. And the condition is that there's too much water vapor compared to what the air can sustain. And so the formation of droplets is nature's way to get rid of these extra droplets. And so when you're creating these droplets, you should expect that the conditions that made these droplets necessary would come less, right? So you should expect that the condensation has an effect on the saturation itself. And this opens up some interesting question, because if droplets can have an effect on the environment, what is that effect and how can we quantify it? Now, this question would be extremely complicated in abstract, but right now we're only considering liquid droplets, and we're only considering the processes that can affect these droplets. And these, for now, are the nucleation and condensation, and also evaporation, of course. We're not considering collisions. We're not considering the ice phase and whatnot. So only these two things. So we could begin by asking a very simple question: how is the saturation ratio? Okay, which I remind everyone, saturation ratio is vapor pressure over saturation vapor pressure. How is this going to change in time? Okay, let's assume that we have a cloud that is going up, okay? A cloud that's going up, the z-axis. How is this going to change saturation in the environment? Well, simplest way to do this is to start by writing a time derivative of supersaturation, and then this would contain some production term and some quote-unquote destruction term. What is the production term? Well, I mean, you're going up, so you are pushing a parcel of air into colder and colder air. And colder air, remember, you remember your good friend, the Clausius-Clapeyron equation, which I remind everyone. Is this guy here. Colder and colder air means that you'll be, the E star will also decrease, okay? Will be much lower. As you go up, E star will be decreasing, okay? As you go up. The Clausius-Clapeyron equation is probably not particularly informative, but if you look at the solution, take one step further, this tells you that the logarithm of E star should go like 1 over t, okay? Minus 1 over t. And so at colder temperatures, you should expect E star to decrease. That means that the air is able to withhold even less water vapor, okay? So this produces saturation as you're going up. The destruction term is this guy here. It has a minus because it reduces the saturation ratio. And for all intents and purposes right now, that is simply the condensation term. The destruction term is due to condensation processes, okay? Okay. This is all great, but so far it's still kind of useless because eventually we'd like to compute this, to turn this into something that we can use to make calculations. So let's make a step forward and let's try to see if we can turn that into a more explicit formula. We will start by assuming a two-step process, okay? First, we're assuming a parcel that is ascending, but without condensation, okay? So let's assume that the parcel is going up, and let's assume that the parcel is going up by some infinitesimal amount, okay? In this infinitesimal amount, no condensation happens, okay? Excellent. So in that case, we can write in that case, the condensation term is 0, okay? Because we're assuming no condensation. Because S is E over E star, the differential ds would be dE, would be ds over dE, okay? Over dE times dE plus ds over dE star. dE star, this is just how you take differentials. This first derivative is trivial, really, right? Because you're just taking that out. And so this is 1 over E star. Actually, let me write it down here. This is equal to 1 over E star times dE plus derivative with respect to E star. That's a little bit more complicated, but not that much complicated. dE star squared dE star. So if you collect the 1 over E star squared at the beginning, this is simply E star dE plus E dE star. Just kind of nice and symmetrical to some extent. Okay, excellent. Okay, now because we're interested in temporal changes, this is not very rigorous and kind of hand waving, but trust me, you can do this. You can divide by dt, even though it's not exactly a division because derivatives are limits, but this still holds true. Okay, excellent. So we turned a derivative of the supersaturation, which I don't know in principle we didn't know how to do. Okay, I'm gonna erase this because we have it written anyway on the slide here, and we can start seeing how we can start to see how d over dt and d star over dt can be computed. Okay, let's start with d over dt. The first thing you have to keep in mind is that in this case, is that in this case, we are assuming that there's no condensation going on, right? And so the mixing ratio, R, this, I remind everyone, is written as epsilon E over P minus E. This can be approximated generally as epsilon E over P, okay? Because P is much greater than E, okay? Excellent. Now, we can do a similar process and compute dr, right? And this would be derivative of R with respect to E dE plus dr over dP. Now, because there's no condensation, the variation of this is 0 identically, okay? dr over dE, this is pretty simple, is epsilon over P times dE plus dr over dP. I mean, it's the same calculation, you know, it's a very similar calculation to the one we did before, right? And so this is minus epsilon P squared times E times dP. And this is equal to 0, which means this you can take out, assuming P is not 0, and that's usually not the case, dE equals E over P dP. Excellent. So we can proceed and substitute it, right? I think this is a plus. My apologies. Okay. Excellent. Okay, so now dE over dt, where can we write it? dE over dt has become E over P dP over dt. Now, two more things here. First is that the ideal gas law still holds. And so P, write it here, is still equal to density of the gas, rho, times R prime, this is the gas constant for the air, times T, right? And so we can substitute it. So this is E over rho R prime T dP. This is a prime, yeah? Excellent. But we're also assuming the hydrostatic approximation. I remind everybody, this means that infinitesimal changes of pressure are minus rho G times dz. This is gravitational constant, equals more or less, yeah? 9.81 meter per second squared. Okay, so substitute dP in here. The rho cancels out, and this gives us minus E G R prime T dz over dt, which is exactly what I wrote here. Over dt. Okay. Excellent. Okay, but what's the advantage of having something like this? Well, the advantage is that what is dz over dt? All right, we have a parcel that's going up. dz over dt is the parcel's vertical velocity. So now you turn something like temporal changes of vapor pressure changes of vapor pressure over time. Now you turn it into something that you can more or less compute. Vapor pressure, T, and the vertical velocity. Just pretty neat. Okay, excellent. Now the slide is becoming a little bit crowded, so we get rid of this. Hopefully you took note. If not, I mean, this is a video, so you can always go back. That's the beauty, really, of doing something like this asynchronously, so you don't have to, take pictures of a whiteboard or whatnot. Granted, I would much rather see you face to face and be in class, but again, current conditions don't quite make that possible. Okay, the second term, so this is done. This is taken care of. This, well, we still don't know what it is, so let's now deal with dE star over dt, all right? How can we do that? Well, remember our good friend, the Clausius-Clapeyron equation. Okay, so if you do that, if you use Clausius-Clapeyron equation by Clausius-Clapeyron equation, this was L E star over RV t squared. Now dt over dt, which also reminds me that before here I was being very confident in writing this formula, but I got these factors wrong. Sorry, I apologize. Okay, excellent. Okay. I was trying to think if there's a good way, a good mnemonic way to keep the Clausius-Clapeyron in mind with the right factors. I mean, in general, when there's a t, chances are that if you have to pick between these two, it's always a gas constant that's going to be close to it. But then again, I don't know that I would elevate this to like a universal law status. So yeah, let's just try and memorize this formula. Anyway, okay, so we turned this into something a bit more tractable. Now dt changes in temperature. Here we're going to make one more assumption, and for sake of simplicity, we're going to assume a dry adiabatic lapse rate. Okay. In the tropics, this is not quite true because the lapse rate is moist adiabatic usually, but yeah, for the sake of simplicity, let's assume that. That, I remind everybody, dt over dz is minus g over cp. That's the dry adiabatic lapse rate. This is about 10 meter per second square. This is about 1,004 joules per kilogram per Kelvin. You put everything together. I think this is joules per Kelvin, not per kilogram. You put everything together, and this is about 10 Kelvin per kilometer. Okay, just what we know. Okay, so now dt, you change it with this, and this becomes minus L E star over RV t squared times g over cp times dz over dt, which is brilliant because now this dz over dt is also what we had here, and so we can collect both. Okay, put everything together, write it down here, and collect the dz over dt. And perfect. So the first term, the production term, now we've got it. Okay, now we know how to write it in terms of simple, quote unquote, simple variables that you can compute more or less easily. Okay, and the vertical velocity, which, maybe you can measure, maybe the model tells you what it is, and maybe you can put in some rough estimate. Excellent. Now for the second part, which was the destruction term, or the condensation term, if you will. Okay, how do we compute that? We start again from this, but now we're assuming that we're not moving, okay? So the parcel is not moving anymore. The parcel of air is here, and it's starting to condense. So condensation is now happening, but there's no motion. So trying to get this, to turn this into something like F times dz dt, it won't do us any good. However, now we're condensing, we're not moving, and so we're producing liquid. And so it may be turning it into something that depends on not so much z, but for example, the liquid water mixing ratio. This may be a more useful thing to do, yeah? Okay, and in particular, we can start again with the first term here, d over dt. Okay. Now here we just simply use the ideal gas law for water vapor. So E is rho vapor RV T. Okay. Let's assume this is not quite true, but let's assume for the sake of simplicity that only that the temperature is not changing. Okay. And so this is going to become something like rho V over dt. times RV times T. RV, remember that this could also be written in terms of the gas constant, R prime over epsilon, and which is what we have here, okay? Now, this will become, it's clear why this is useful, because now rho V, the d rho V, the changes in the water vapor mixing ratio now can be related to changes in liquid water mixing ratio, and this is exactly what we want, okay? The second term that we are going to deal with is this dE star, and start again by writing down by using the Clausius-Clapeyron equation, and then we do then we do another step, which is if we assume that the Moist static energy remains constant, then Cp dt plus LV dQV equal to 0. And again, dQV can be related to DRV, which can then be related to DRL. And so this gives you something to turn dt into a DRL. And if you do that, this is what you end up having. You put these two things together and you get to this formula. Okay, this is the destruction term. Notice that now, as we want it, this depends only, well, it depends on DRL, changes on the liquid water mixing ratio. Finally, let's put everything together. To summarize, we have this formula here, where you have some factor times dz over the dt, vertical velocity, and that's the production term, minus a destruction term that is proportional to, again, a factor, Q2, which we determined, times dr dt, which is the condensation ratio, if you will, the condensation rate. Okay, so this is great, because if we put this together with what we had before, remember we had a formula dr squared over dt, where r now is the radius of the droplets. Now, with this, we could compute pretty much everything, because this tells us how the radii change S. And now we can compute how S is changed by, the motion of the parcel and also the condensation. The condensation will affect the radii of the particles, of the droplets. And so these couple systems could in principle be able to predict exactly what happens in the cloud and in the environment. Okay. So in principle, you could start with a spectrum of droplets, and you can compute exactly what's going to happen to these droplets, right? Because as you start condensing, that will affect the supersaturation within the environment, and that will in turn affect how the droplets will grow. Okay. The figure here, this is from a very old paper from 1959. The figure here shows the fate of droplets at various radii as they ascend. As they ascend in the cloud. This is roughly where cloud base is. Okay, at 800 hectopascals. Notice that we're going up in logarithmic scale, and this is also in logarithmic scales. This is the radius of the droplets in micrometers. And also this dashed dotted line here shows the supersaturation. Okay, so this is S minus 1 expressed in percent. Okay, so notice a couple of things. That first thing, as you enter the cloud, these are meters above cloud base. Again, logarithmic scale. 1 meter above cloud scale, above cloud base, you start to grow. You start to notice some changes. And above 10 meters, and supersaturation begins to increase, right? So you're going into colder and colder temperatures, and so you should expect supersaturation to increase, as we said before, right? Okay. As we keep rising, however, supersaturation gets to the point where now it's so high that cloud droplets start to be formed, okay, and start to grow by condensation. And notice that when that happens at about 10 meters above cloud base, the supersaturation then drops, okay? And also notice that about 10 meters above cloud base, there's kind of a discriminatory behavior whereby droplets above a certain size, above a certain radius, sort of 0.1 micrometers, more or less, these will grow rapidly. Okay, and they'll keep growing until, micrometer, 10 micrometers. Here is about 10 micrometers and so forth. Droplets that were smaller than 0.1 micrometers, about 10 or 50 nanometers, these will remain more or less untouched. Okay, they grow a little bit, but then they start decreasing. Okay. So they grow a bit and then they start to evaporate after supersaturation has reached a maximum. Notice that supersaturation never really does get above 1%. Okay, so remember when we said, one of the effects of cloud condensation nuclei is that they allow for condensation to happen before supersaturation gets too crazy. Well, this is a perfect demonstration of that, where you go at like 1% and that's already enough. Okay. Now, the next topic I wanted to introduce is that we thought about droplets as an individual droplet, or a collection of more or less individual droplets of a certain radius, and we computed some equation for this radius. Okay, but but droplets actually are typically what you have in a cloud is a population of droplets with various radii. And so, for example, a cloud base, you'd have a distribution, for example, like this, right? Where this is some distribution function. And because of what we saw in the last slide, okay, this distribution will experience some changes. At a later time, small droplets will disappear and droplets will increase in radius. So this may have, a different shape as we grow in time or something like that. And so is there a way to predict, instead of thinking about individual droplets, is there a way to think about the population of droplets? Okay, so the first thing that we want is we can make some simple estimates, actually. And if we go back to the equation that we wrote before for ds over dt, we can compute some interesting properties. Okay, let's go back to ds over dt, and let's assume that these quantities do not change much. Okay, where is this maximum reached? Where is the maximum of supersaturation reached? Well, or better, at which conditions is the maximum of supersaturation reached? Well, when that is reached, it means that this quantity here equals to 0. And let's assume that omega and eta, they can be related to, they are related to properties within the clouds, and these factors remain constant, right? So under that condition, this simple model that we had does have a steady solution, right? At what supersaturation is the maximum achieved, right? This you put equal to 0, and you solve for S, and S is literally omega over eta, and you have all the ingredients to compute it. Then you compute this, and you see that the limiting supersaturation according to our model is 0.5%, okay? And this is reached right above cloud base, okay? So this tells us something about the population of the droplets, right? Because when you reach this degree of supersaturation at 0.5%, this is where supersaturation is maximum. And this is more or less where sort of this different behavior for the droplets change, right? So this introduces some scale for the variations of the radii, right? At this point, you know, when supersaturation, according to our model, reaches 0.5%, then you start noticing changes in this population, okay? Okay, so can we, assuming that this is what's going to change, this is what's going to happen, and assuming that that's the point where things start to get serious for the droplet population, and where we start noticing changes in the distribution of the droplets, can we say something about how the population of droplets will evolve? Not from the point of view of individual droplets, but really from the point of view of the whole distribution of droplets. Okay, how is the distribution going to change? So in other words, before I wrote this down, right? This was some distribution function, radius, and this was some distribution, actually, to be consistent with what I'm going to use later. We'll call this function nu. Okay. And nu is a function of the radius. This is a distribution function. Okay. Now, stop thinking about individual droplets and how these will change, and think about this guy here. So this is the main character of the story. How is this going to change? Okay, this is almost your physical variable, if you will. Okay, and so this distribution, or probability distribution, according to how you normalize it, what this tells you is that if you take a small column like this of width dr, then this tells you how many particles have a radius between r and r plus dr, where r is some variable, some value, okay? And dr is the width of this column over here. This is what we want to understand. So instead of taking one droplet, let's consider all the droplets that have the same radius, or, you know, that have similar enough radius, meaning all the droplets that are contained in this column. Okay, what is going to happen? Pardon my my terrible drawing skills. What is going to happen? This is getting bigger and bigger because I don't know how to draw. Let me just redraw it, just not to confuse everybody. Okay, down like this, and okay, let's draw a small column. Okay, promise I'm not going to touch this anymore. Okay, so what's going to happen to this column over here? As condensation continues and these droplets grow, what is going to happen? Okay. First thing, nu dr is what we care about, okay? And we want to know how this is going to change in time, okay? Well, first thing is that this rate of change is going to be equal to this quantity here, okay, by conservation. This quantity is the flux, the net flux of droplets that come into this column, okay? Let me write this like this again. Actually, I'm exploring drawing tools of PowerPoint as I go along. Okay, so we care about this column, right? So and I represents a net flux, okay, into this column. Again, think about this as almost a physical space, and you're thinking about a flux into this column and out of this column. And the difference between the two is the net flux. What does this net flux mean? What is this thing, right? Here I said current, but current is pretty much the same thing, right? So imagine that you have a parcel here, okay? And the parcel will contain droplets of various radii. There will be small droplets, larger droplets, really, really big droplets. Okay. Excellent. And so some of these droplets, I'm going to color them in red. Some of these droplets have the radius, which is what's we're contemplating right now. The other droplets are either too small or they're too big, right, to be to be considered in this infinitesimal column, which I'm going to expand a little bit. Okay. Thought it would be a bit bigger, but whatever. Okay, so as time changes, some of these droplets are going to get bigger. So these two guys may get bigger, and they will leave the column because this column represents droplets that have a certain radius. If these guys get bigger, they're not going to have that radius anymore. So let's say that this guy over here gets too big to be considered in this column, right? And so, how do I undo the color? And so this will get bigger at the next time step. And so this will leave the column. And so this will be sort of a net decrease in the number of droplets. But maybe in the next time step, this droplet here and this droplet here will have the right radius to be considered part of that column. So let me redraw them with a bigger radius. Maybe this have this radius and this have this radius, and maybe these two will have the radius to be considered part of that column. So we lost one droplet, but we gained two, okay? The other ones, this didn't grow to be big enough. This didn't grow to be big enough to leave the column. These two are too big, and these are small, so whatever. So we lost two. So, pardon me. We lost one, but we gained two. And so the net flux is that this will increase by 1 at the next time step, okay? So we'll actually get bigger. So this is what I mean by flux in and flux out, the net flux into this column. Some will come in because they get big enough, and some will come out, okay? Because they're too big, okay? Now, this function here, we can write it in simple terms as essentially a function of the radius, okay? And if you put everything because you can think about it as a current through space, you can write this essentially as the change of the radius with respect to time, okay? If you put everything together, what we wrote down before, and this hypothesis here, then you get to this function, to this differential equation. The partial derivative of your function here, of your distribution function, is given by the derivative over r, so over this dimension, of how much the radii are changing. Now, for steady supersaturation, do you remember the equation? Well, you probably remember the equation by now. R dr dt equal to s minus 1 fk plus fd. Let's assume that this is some constant, c, which I'm not sure is how you're supposed to write c, but whatever. Okay, so divide by r, and so dr over dt, you can assume is c divided by r. Okay, so we make this simple assumption. So put that back there, okay? You take a derivative, and this gives you a simple way to solve this equation. And if you solve the equation, you get to something like this, where nu 0 is the initial distribution, the distribution of radii at time equals 0 when you entered the cloud from Cloudbase, okay? And so provided you know what this is, then you can know, with some assumptions, you can know, or you can have some kind of understanding of how nu will change as a function of time and also of radius, of course, okay? So once you know the evolution at the initial time, you know it for all the times. This is probably not the best because you still have to know this, but still, I mean, it's some kind of progress, okay? So we're kind of happy. Okay. One thing that we need to keep in mind is that obviously this is good to have some kind of basic understanding of what's going on within the cloud. But if you were to, do some very precise, calculations, then you cannot use this because we made far too many assumptions in deriving this formula. And this is true not only for this formula, but for all the formula that we derived so far. Look, unfortunately, this is a set reality that we need to face, but unfortunately, the reality itself is very complex. And so you either can't say anything useful about reality, or you have to make a lot of approximations, right? So you either need a computer to compute everything, but then you don't understand why things work the way they do, because computers are going to give you a solution, not a reason, an intuitive reason why the solution exists. So you either have that, or you're going to have to make a lot of assumptions, okay? And yeah, reality is complex. So, and particularly in atmospheric sciences and climate science in general, climate science is a complex science, which means that there's no way around it. You can't neglect the complexities of reality the way that theoretical physics does, for example, right? And so that means that all the formula that we derived are very, very simple, but also very approximate. And so we need to take into account the fact that the calculations that we made, the formula that I showed you, are approximate. There are ways, more or less empirical ways, to show what these formula would look like if we took into account corrections. And this is kind of the real work of a scientist, which is to take the beauty of mathematics and corrupt it with a little bit of reality. And there are ways to start accounting for some of the factors that we ignored, and start to account for these, and make sort of stretch the formula a little bit closer to reality. One thing that usually helps is to think about limit cases. Okay. In limit cases, it's typically possible to make some kind of simplifying assumptions again, and desimplifying assumptions are reasonable because maybe you can expand in Taylor formula, like the way that we've done in previous lectures, and higher order terms can be safely neglected. Complicated things happen when these, when you can't go to the extreme and you have to compute things. But, as long as you can go to the extreme, then you can do that. A lot of times in what we do, what dictates whether you can go to an extreme or not are length scales or time scales. So once you introduce a scale, then that can dictate whether you can go to some kind of extreme. Because we're dealing with gases, the mean free path is your typical length scale, okay? Or at least it's one length scale that you want to take into account. Anything below the mean free path means that you really have to pay attention to what's going on at the atomic level, okay? And you have to use a lot of quantum mechanics and really complicated stuff. The other thing that we care about, because we are dealing with clouds, the other scale that we could introduce is the cloud droplet radius, okay? So we have two quantities with units, and they have the same unit, the mean free path, L or lambda, however you want to call it, and the cloud droplet radius. You can form a dimensionless quantity, a dimensionless number known as Knudsen number, and the value of this number dictates in what regime you are. So when the cloud droplet radius is much, much greater than the mean free path, in this case, you're dealing with really, really large droplets. And these droplets, they're looking around and they're seeing a continuum. Much like when you look around, the air to you, the air looks like a continuum to you. The ocean water looks like a continuum. Everything looks like a continuum, right? Like a solid, a gas. It looks like something that knows no gaps, okay? And so in this case, the equations that were derived are more or less, they're okay. Because you can use, in this case, you can use thermodynamics. You can use the ideal gas law. However, when R is much, much smaller than the mean free path, in this case, the droplets are really small, and they're not seeing a continuum, but they're seeing molecules of air as giant molecules, as giant balls. And in this case, we're still kind of lucky because we can use some, molecular diffusion theory and make some simplifying assumptions, again, because we are in the opposite extreme. And so we're lucky in this case. But when the droplets are more or less similar to the mean free path, it means that the droplets are not big enough to see the continuum, but they're not small enough to see air molecules like giant balls, okay? But instead, they're kind of the same. And that's where the trouble is, right? Because you can't make any simplifying assumptions. All the terms, if you were to expand your formula into a Taylor series, all the terms would be equally big, right? Whereas whenever you expand in a series, you like expanding in series because typically the next order is smaller than the previous one, right? And so by that degree, usually orders get smaller more rapidly as you go to higher orders. And so at some point you can just say, hey, I'm cutting at second order, at first order, or whatever. But in a case where all the terms are equally important, you can expand in Taylor series, right? And so for this case, there was an approach that was developed many years ago. And the approach essentially requires two parameters. Now, we're not going to use these corrected formula. We're not going to use these corrected formulas. So we don't really need to go through the derivation. We don't need to know all the exact details, but sort of get some appreciation for how these things are done, right? These corrections are done. Okay, so the first parameter is called an accommodation coefficient, and is denoted here by alpha, and then a condensation coefficient beta. Alpha is written as the ratio between two temperature differences. The first one is the difference between the temperature of vapor molecules that leave the surface of the liquid. Suppose you have the liquid droplet and you have a bunch of molecules that are leaving. We assume that these have temperature T2 prime. T1 is the temperature of the vapor, okay? And T2 is the temperature of the liquid droplet, okay? So if these molecules that are leaving had the same temperature as the droplet, then they'll be able to leave, and alpha would be 1, okay? This, however, is not always the case, right? We think of molecules as droplets as small, but In reality, they're formed by many, many molecules, and there definitely are temperature variations within each water droplet. And the condensation coefficient beta is the fraction of molecules hitting the liquid surface that eventually condense, right? These hits, condenses, and so it becomes part of the liquid droplet. Okay, with these two assumptions, the formula that we had originally derived together, RDR over DT, which you're probably going to be nauseated now to see show up once again. Now, what these two parameters do is introduce two factors, two functions, okay? And these functions depend, one on the accommodation coefficient, the other one on the condensation coefficient. And these are relatively simple looking functions, right? Where, these are just rational functions. But these kind of length scale, L of alpha and L of beta, they're relatively complicated functions of parameters related to the droplet and related to the environment, okay? So the first correction that we want to adopt is that when the droplets have a similar, they're small enough to have a similar, to be kind of considered gas-like, okay, then the growth of the radius is a little bit modified by that, right? Okay, it's modified by the fact that you're not surrounded by a continuous vapor, but you're surrounded by a discrete medium that's made of a finite number of molecules. Another assumption that we had made, but that could use some correction, is that we had assumed that we have a droplet here, we have a vapor field around, and the vapor field is more or less symmetrical, right? You go 360 degrees around the droplet and nothing really changes. Well, that is kind of true for droplets at rest, but remember that some of these droplets are moving inside of a flow. So some of these droplets, for example, are inside of really strong updrafts, or if these droplets are big enough, these are liquid droplets that are falling in a rain shaft, okay, in a precipitating column. And when you start entering some turbulent regime, then this assumption is not true anymore, okay? And so when the Reynolds number is large enough, then you can use some correction term to the Kelvin equations. Okay, so this is another type of correction that you can make. Another type. Okay, yeah. So the Reynolds number. I'm assuming you're all more or less familiar with the Reynolds number, but the Reynolds number around the drop can be defined in terms of these basic quantities: the radius of the drop, the density of the vapor, falling velocity, and mu is the dynamic viscosity of air. And so, for example, for a drop of 20 micrometers, Reynolds number is about 1.06. For 40 micrometers is 1.25. So larger droplets. For larger droplets, the growth by condensation is negligible, as we will see in a few lectures, and so ventilation effects like this one can be ignored, can be neglected. Another correction that we may want to take into account. Again, also just a reminder: you don't have to memorize. You don't have to memorize all these things, all these numbers, because in all these formula, you don't have to know them by heart, because, if you ever want to know these things, you can always look them up at a table when you need them, right? But just keep in mind that there are these correction terms. Another correction term is the fact that the fields of the thermodynamic fields around a droplet are also not steady, right? Because the droplet is changing its shape, because you may be in a different part of the environment, and there may be some inhomogeneities, and so it is safe to assume that the growth is not typically stationary, okay, because the drop moves around. And so you may be in places where you have more or less water vapor as you're moving in a turbulent flow, right? It's all good when you're in a lab, but for real clouds, you have to take these things into account. The updraft may be unsteady. So again, the updraft is a highly turbulent field, right? And so you may expect that there will be weird things happening to the updraft. The velocity may change very, very much. Also, even if the updraft, let's assume that this is the flow of the updraft, right? For whatever reason, let's say that the updraft curves because it's going into some turbulent eddy. If you have a large droplet that is flowing with the updraft, the large droplet can have such a big inertia that as it travels, instead of curving, it'll actually keep going and go into another part of the flow of the updraft that may have, I don't know, some eddy going some other direction, right? So you're in a highly turbulent field and you have pretty heavy sometimes droplets. And so you have to take all these effects into account. And finally, we call these statistical effects, corrections due to statistical effects. And this is due to the fact that we are assuming that things are well behaved, because otherwise things wouldn't be tractable mathematically. But in reality, things aren't really all this simple, right? And often you might expect that droplets experience constant changes, constantly changing fields, like I showed you before. One way to account for these things is to just assume that you have a population of because you have a population of droplets, right? You have a whole population. You may assume, cannot turn negative. You may assume that some of these, it's quite likely that some of these will experience a variety of conditions, and these can be described by other distribution functions of like temperature, water vapor, velocity, and whatnot. So you could also think in terms of statistics, right, and kind of estimate a probability that these effects matter. When you have a large cloud and you have many, many particles, then statistics may actually not be a bad way to go about. It's not going to solve all the problems, and there are some questions that still remain open, but still, I mean, this could be something to take into account. Okay, I think this is pretty much all I had to say to you, or all I wanted to say to you about the growth of droplets by condensation. Next time, we will talk about something that we experience every day in Hawaii, which is rain. And particularly, we'll talk about initiation of rain in warm clouds or non-freezing clouds, which again are kind of, our good friends here in Hawaii. I hope you enjoyed this lecture. As usual, please let me know if you have any kind of question about this. Send me an email, call me up on the phone. Please get in touch if you have questions. Otherwise, I'll see you for our next lecture.